Live. Welcome everyone to our webinar this evening entitled What is the Rigor in Mathematics Education? It is being presented by Nevels. Nevels has been the math coordinator of the Hazelwood School District in Missouri since 2012. He previously worked in the St. Louis School District where he has served as a teacher, departmental chairman, district curriculum writer, and technology trainer. Additionally, he has developed mathematics curriculum at the district level and has trained countless teachers to understand and implement the district curricula and technology plans. Nevels earned his doctorate in mathematics education from the University of Missouri at Columbia in 2012. His research dealt with integration of technology into the mathematics classroom, as well as thinking, teaching, and learning in mathematics education. He is a member of the Casio Teacher Advisory Council. So without any other interruptions, here is Nevels.
Okay. Well, welcome everyone. This is What is Rigor in Mathematics Education? And this talk is basically inspired by an article by current NCTM president Linda Gojak. Sometime around in February, she wrote an article talking about what's all this talk about rigor. And this presentation has been inspired by that. Basically, the word rigor is widely used in policy discussions, but is rarely understood or defined. And it often merely passes as code for better. What's more interesting is that the term rigor does not appear in the Common Core State Standards for mathematics, although it is certainly implied. If you were to go online and look up a thesaurus and ask for synonyms for rigor, you'll come across words such as these: friction and flexibility, difficulty, severity, rigidity, suffering, and traditionalism. Surely these are not what we mean when we talk about rigor in the classroom. Okay. Her article goes on to talk about moving towards rigor. And I briefly give a few bullet points that talk about rigor here. The days of a few word problems at the end of the multiple skill exercises in the book are over. Concepts must be introduced and explored in contexts that are interesting and motivating for students. That's a weird one. Rigor lies upon whether or not your concepts are interesting and motivating. Okay? Tasks must provide entry points for all students, offer them well-defined opportunities to make connections to other mathematics, that's really important, and include both opportunities and expectations for them to develop deeper understanding. And finally, the focus and coherence of the Common Core State Standards gives us a pathway to rigorous instruction. Okay, so let's begin. All right, first I want you to consider this simple equation, okay? Most of us will probably solve this by inspection, but more importantly than just solving this equation, I'm really concerned about whether or not you think this equation or this task is rigorous or not, okay? So we'll use the Casio 115 ES Plus to kind of help us explore this. If you see my screen now, we have the calculator emulator. This screen right here is just a magnification of the screen. So even though I'll do work here, you should probably look here because it's larger. And this window displays my keystrokes. I'll probably be resetting this so that it won't be too encumbered with keystrokes. All right. So one way to explore this is a feature called Calc on this calculator. And this is how we use it. what I'll do is I'll enter an expression instead of an equation. So instead of entering x minus 1, I'll do this. So I have to find the x key. So I'll hit alpha, right parentheses, that puts an x there, and then minus 1. And instead of hitting the equal or the execute command, I'll come to this button that says calc. When I press calc, it allows me to evaluate that expression at any value that I type in. I don't know what this crap is right here. It's 1.619. So let's type in a 5. So if I type in a 5 and then hit equals, what it did was just substitute 5 in for x and evaluated that expression. I get 4. Okay, so that's one way we can explore evaluating equations. But I'm sure most people just by inspection, I'll hit calc and we'll type 1 and we'll evaluate the x minus 1 at 1 and we get 0. Okay, so that was pretty straightforward. All right, so let's do something a little more challenging. Okay. And as we solve this equation, I really want to think about, is this rigorous? Is this equation or is this task of solving this equation more rigorous than the previous task? Okay, that's what I want you to be considering, the rigor. All right, so let's explore this as well. All right, so we have 3x minus 1 equals 0, but I'll use my 115ES plus emulator to evaluate this. So I'm going to clear these keystrokes here so we can start anew. And now I have 3, and then this is how I hit my x. So these two keystrokes, alpha x gives me an x, minus 1. I don't want to hit equal. What I want to do is substitute values in that will help me bring this expression to 0. So I don't know, I'll guess a 5. I guess a 5, I don't get a 0. All right. Let's guess a 4. I guess a 4, I don't get a 0, but I notice that my answers are getting closer to 0. As I decrease my guess, my answers are starting to get close to 0. So let's try a 0. I'll try a 0, so calc, and then 0. Notice my keylog is filling up. All right. I get a negative answer. I actually go beneath 0. Okay. This is one way to use this calculator to kind of help bring meaning to solving some simple equations. Another method that's a little bit different is to help facilitate guessing, since we're just guessing, is to change the mode. Okay. If I change the mode and use a table, so let me clear that out again. Let me clear this, and let me clear all of this, and I'll just hit all clear. I don't know why I hit all clear. Okay, so if I change the mode, I want to go to mode, and it seems to be number 7. 7 is table, so I'll hit 7. So I'm in mode 7 now. Now I can enter in a function or an equation. I can enter that same expression on this side for this function and get 3 alpha x minus 1. And when I hit equals, it's going to ask me for a range of values to evaluate this at. Okay, so let's start low. Let's say at a -3. I could either use a subtraction sign, 3, or I could use this sign. It doesn't matter. So I can say a -3. That's where I'll start. And I'll end at, let's say, a 5. That's great. And this step is saying, how do I want to proceed from a -3 to 5? And I'll increment up by 1. So I'll go from a -3 to a -2 to a -1. So by 1. I can make this step negative or positive, and I can make it a decimal as well. But one whole number is fine. Okay. So here are my values of x. They go from a -3 to a -2, and you shouldn't be looking here. You should probably be looking here because it's magnified here, but if you wish, you can look here as well. And also, if you notice that every time I go down this table, the number here that is highlighted is magnified as well. Okay, so I'm at a -2. I'm at a -1. And as I go down this table, this helps me quickly guess a lot of different numbers all at once. Okay, and I can see as my numbers increase, I'm getting closer and closer to 0. And in fact, I don't have a 0 value, but it seems like my value is somewhere in between 0 and 1. So armed with that information, and I'll clear this off, armed with that information, I can start over and start at 0 and stop at 1 now, and maybe increment smaller. Maybe by, instead of a whole number, maybe by tenths. I'll increment. Now I have values. I can see that my 0 value is in between 0.3 and 0.4. And likewise, I can continue that ad nauseum. So now I have these values 0.3 and 0.4. I can evaluate this between 0.3 and 0.4. And now I'll probably step by 1/100ths. And hopefully this will get our students to start appreciating recognizing decimal expansions. There's 0.33 and there's 0.34, somewhere in between there. This is probably going to be ending up to be 1/3, which we probably saw that from inspection from the beginning. Okay. So when we saw this equation, some of us just by inspection just added 1 divided by 3, what have you, and saw that the answer was 1/3 indeed. But is this question more rigorous than, than this task? Okay, is it more rigorous? So let's look at a third task. Okay. Now we have x to the second power minus x minus 1 equals 0. This one probably could not be solved by inspection, where the other two could be solved by inspection or by manipulating the equation using some, properties, adding things to both sides, subtracting things from both sides. This equation is a little bit different, okay? But we can still use our calculator, handy dandy calculator here, to first hone in on some answers or not, or maybe just guess. Let's see how that looks. So I'm going to change the mode back to the regular computation mode. I'll clear all these off so you can see some keystrokes here. I'll enter in that expression. So that was an x to the second power minus x minus 1 equals 0. But in this case, I want to leave that expression, and then I want to guess numbers that I can substitute into there that will bring me to 0. Okay, so I will hit calc, and I can hit a 5. That's not 0. I can hit calc, and I can hit a -1. That's not 0 either. Okay. Or I could just use my table. So I'll go to table, mode 7, enter in an expression, minus x minus 1, and just guess a range. In this case, I think I want to maybe start at 1 for some strange reason and end at 5. And I want to step by 1. And here's my table. And as I peruse my table, 5 seems too big to make it go to 0. 2 seems too large to make it go to 0. 1 seems too small to make it go to 0. So it seems like my solution is somewhere in between 1 and 2. So like I did before, I can clear this off again. I can start at 1 and stop at 2 now. and increment maybe by 1/10 and analyze my table. Okay, seems like these numbers are too small to make it go to 0. Again, you shouldn't be looking here, you should be looking here. Okay, and I can use the arrow key on my computer as well. Oh, it seems like we have something here in between 1.6 and 1.7. So let's try that again. So I'll go between 1.7 and I'll step by 1/100th and I'll look at my table. And again, you should be looking here. All right, so I'll come over here and I'll look at these negative numbers. And now this is a small number, but it's definitely positive. This is not a negative number. Okay, this is scientific notation. 4.4 times 10 to the negative 3 is still a positive number. So I have a negative number here and a positive number here. So 0 must be in between. So the value that corresponds to 0 is in between 1.61 and 1.62. So I will go one more. So I'll know I need a 1.61. I also need a 1.62. And my last step was 1/100th, so we'll make this one a little smaller. And we'll analyze this table. So it seems like my answer, so again, you're looking here. My answer, these are all negative values. Oh, that's a positive value. This is a negative value. So somewhere in between 1.618 and 1.619, we'll go one more time with A. What are we doing? 1.618 and 1.619, and oh, that's cute. We'll step by, let's say 1/10,000th of a unit. So here we have 1.618, 0, and 1.6181, and it seems like it's negative and positive right at those values. So let's say the answer to this is approximately 1.618. Okay, we're good. All right, one of the answers. Okay, some of you may also notice that this is a quadratic equation, and quadratic equations can have at most two solutions, two real solutions. This one does have two real solutions. We just kind of concentrated on one of them, 1.618, and that's good enough. All right. Okay, let's switch gears. Now, well, let's not switch gears. Let's go back. Hopefully by now you're beginning to understand that questions or tasks in themselves do not possess the quality of rigor, especially those focused on procedures. What you do with a question or task is what makes it rigorous. The connections that you make, the entry points that it has, makes it rigorous. Whether or not it's interesting, whether or not kids can make connections to the task at hand, makes it rigorous. So I want to state that the type of, this question may be more difficult than, let's say, this question, but it's definitely not rigorous. The same type of thinking that's required to solve x minus 1 equals 0 is the same type of thinking and the same depth of thinking that's required to solve this. Now you even know a solution. You may can just remember the solution, and when you see this expression, say it's approximately about 1.618, something like that. That's at least one of the solutions. You at least know half the solutions. Okay, so let's move on now. Okay. Rigor. It says task rigorous. Find a number such that 6 more than the number is equal to the square of the number. Is that rigorous? Okay. Here we have some Common Core practice standards beating right out of us. Mathematical Practice 6 talks about attending to precision. And this may be an issue for some when it comes to understanding the expression square. What does the square of the number mean? Okay, or translating these words into to make it into an algebraic sense that you can manipulate and solve. Okay, here's a very neat feature on the 115EX. This is a very powerful feature. So I want to change the mode to something that's not being displayed here. There's an arrow here indicating there's more options. And this is called the verify mode. So mode 2, and I'll clear here. All right. And what happens in the verify mode is I can enter in a mathematical sentence, and it can determine whether that sentence is either true or false. So for example, I can say 1 is equal, the alpha calc gives me my equal, to 3 plus 5 minus 7, and hit the equal, and it tells me that's true. Yeah, 1 is equal to 3 plus 5 minus 7. Okay, we can verify. I can do things like this. 3 is equal to, let's say, the log base 2 of 8. Is this equal to 3? Oh, that seems to be true. Okay, that's working out pretty well. But I can also do things like this. 4. And this button right here, 6, has the command verify above it. So if I hit shift verify, now I have access to my inequalities and equalities. And so I can say 4 is greater than 2, let's say, to the 3rd power. And I'll get a false. No, 4 is not greater than 8. Okay, so that's loosely how the verify command works. So if we use that verify command to maybe help us walk through this problem, which has a lot of, it's very open-ended. This one has a lot of ways that you can approach this task. But we're looking for a number such that 6 more than the number is equal to the square of the number. Okay, so let's try this one. Let's try the number 1. I want to know if 6 more than 1 is the same thing as the square of 1. Right? 6 more than a number is equal to the square of the number. I didn't like that one. Okay. Let me try a 3. Let's try a 3. Okay. Is 6 more than 3? Is that the same thing as the square of 3? I like that one. So 3 is a great number. All right. Okay. So the question is this question rigorous? Okay. And most of you maybe have seen that this question actually had 2 solutions. Both a 3 or a -2 will suffice, because we have 6 more than 3 is 9, and 6 more than a -2 is 4. So both a 3 and a -2 will suffice. Okay. Was this question rigorous? Okay. And whether it was rigorous or not, I'm really more interested in this question right here. So this is the same question, okay, but I'm going to do something to it. What I'm going to do is change something about this question and see if I can change the rigor in this question. All right. So here I have find a number such that 6 more than the number is equal to the square of the number. All right. So watch this word change. Boom. See that word change? I changed the word 6 to the word 1, okay? That's all I did. I changed one word, okay? Now let's see if this one's more rigorous. So now instead of 6 more than a number, I just want to know 1 more than a number, okay? All right, let's go here. All right, so we'll stay in the verify mode. I'm looking for a number. Let's start with 1, such that 1 more than a number is equal to, let's say, the square of the number. Doesn't like 1. Let's try it 2. Let's try 2, okay? So 1 more than the number 2 is equal to the square of the number 2. Doesn't like 2. This doesn't seem I don't know what you guys might try, but this does not seem to be in a very effective way of approaching this problem. So the question is changing one word in a task, can that make it more rigorous? I mean, it sounds preposterous, sounds ludicrous. Changing one word should not change the rigor of a problem. Maybe this problem is more difficult, but definitely not more rigorous. And I think we confuse difficulty with rigor a lot, okay? Sometimes we use the word complexity to mean difficult, but sometimes we talk about complexity as a descriptor of the task, and sometimes we use complexity as the descriptor of the type of thinking involved in the task. So there's kind of a lot of confusion there. But I would argue that this problem is no more rigorous than this problem with the 6. This problem with the 6 is more accessible. You can approach it in maybe a few more different ways, and it's probably accessible to younger children, versus this problem is probably less accessible to younger children, but it's not more rigorous. The question or task is not more rigorous, okay? All right, so let's move on, okay? So one way to think about, so let's talk about other methods of solutions to this 1 more than the number is equal to the square of the number. One way is to express these words symbolically, Here we have 1 more than a number, x, is equal to the square of the number x, okay? And if that's true, that they're equal to each other, then their difference must be 0, Or I can just isolate things on one side, or I can think about if 2 things are equal to each other, that means if I subtract those 2 things, then their difference should be 0, okay? So I've taken my x squared and I subtracted my x and I subtracted my 1, so hence the sign changes here. And the difference between these 2 expressions should be 0. This looks familiar. Looks like we've already solved this. At least you have one solution, right? This is our 1.618 guy floating around. So in this case, this question was pretty easy, at least for one of the solutions, okay? All right. Don't want to go there. I want to go here. So now let's change up a little bit. Let's take the opportunity to talk about a nested radical. Now, nested radical is just anytime you have a radical inside of a radical. And that could be a finite number or can go on infinitely, okay? All right. One approach to solving this equation right here is actually using a nested radical, especially if we look at that first line. So here we go. We take that first line, and if we take the root of both sides, the second root of both sides, and simplify that, and yes, I'm leaving out a side. So here I'm only looking at the positive side. I'm not looking at the negative side. We take the square root of x squared. You should get plus or minus, what have you. But I just want to concentrate on one question, one answer right now, just like we concentrated on the 1.618 and did not find the other root or the other solution. And so here I'm on my third line here. Now I have a variable x that is defined, and x is equal to the square root of 1 plus x. So I can substitute what x is equal to for this x right here. This x is equal to itself. It's sort of like it's using its own self to define itself. Since I have x is equal to 1 plus, I'm sorry, x is equal to this root of 1 plus x. This x becomes the root of 1 plus x, and this x becomes the root of 1 plus x ad infinitum, okay? So one way to solve this is to evaluate this expression. If there was some way I could evaluate this expression using a scientific calculator, that would be great. Well, lucky us. All right. So let's go back to the comp mode, and let's clear all. And here we'll have a radical button here, and we'll just create this nested radical. All right. This is called a natural math display. I'm losing my radical right here. And as I build this expression, it looks just like it would look in a textbook perfectly. Trying to do this on a calculator that does not have natural math display would be crazy, because you would have to know where you would stop, and that would dictate how many parentheses you would be putting on the front side to close them on the back side. You know, just try this. Try to create this expression and not know how many radicals that you want to put there. You'll see what I mean very rapidly. Okay. So here I've built this to, I call this a 1, 2, 3, 4, about 5 stacks. I'll evaluate, and you'll see that we're getting, you know, this is like 1.6, it's not 1.618, but let's say if I replay, come back in this radical here, and start adding a few more. Radical 1 plus root 1, add a few more, we start getting close to that 1.618. So hypothetically, or theoretically, you can probably imagine how, as I continue to add more stages in this nested radical, it will probably converge to our 1.618 or what have you. Close enough, okay? All right. So here we have nested radicals as one way to bring to a solution of what number is one more, what number is equal to, one more than what number, I'm sorry, is equal to the square of the number. And so forth. We have this 1.618, okay. Oh, continued fractions, okay. So in a continued fraction is basically a complex fraction. But pretty much it kind of goes on forever. So here's a picture of a continued fraction right here. I should have some ellipses here, dot, 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 to go on forever, forever, forever. But it still is a very complex fraction, but this is what we mean by a continued fraction, okay? So let's start evaluating this continued fraction in stages. All right, let's do that. All right, so what I'm going to do is build this continued fraction. So I have 1 plus, and I need this template here to create my fraction. 1 plus 1 over 1 plus, let's say, 1 over 1. Let's build it there. That seems to be 3 over 2. Okay. Let's erase back and see what the other ones were as well. So let's do this one. That seems to be the number 2. And let's build it back now. Okay. plus 1 over 1. That was 3 over 2, okay? So now let's continue to build. Let's say plus 1 over 1. That's 5 over 3. That's 5 over 3, 5/3, okay? Let's evaluate 5/3. This number will evaluate 5/3. This is 5/3 an exact value. This is a decimal approximation or exact value decimal-wise, 1.6, okay? All right. Now let's go one more. It's my continued fraction, which is basically a complex fraction. We get 8 over 5. Let's evaluate that. It's 1.6. We're still kind of ending up with this kind of 1.6 thingy, okay? Let's do it again. We get 13 over 8. 1.625, okay. That's pretty clear. It seems like this expression here, this continued fraction, this complex fraction, will probably converge to our same number that we've been talking about. Hey, you guys heard of this Fibonacci sequence. Fibonacci sequence is one example of a recursive sequence. A recursive sequence is a sequence that each successive term is determined by one or more previous terms. In this case, we begin with 1, 1. We're just giving 1 and 1. And to get the third term, we add the previous 2 terms together. So 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5, and then 3 plus 5 is 8, and so on. So 55 and 89 is 144. And if I want the next term, I add 89 and 144. Okay? But if I begin to make fractions with the terms in Fibonacci sequence such that it looks something like this, like 1 over 1 and 2 over 1 and 3 over 2 and 5 over 3 and 8 over 5 and 13 over 8 and 21 over 13 and 34 over 21. This sequence right here is the same sequence we get when we were evaluating each term in this continued fraction. You know, when we just looked here, right there, we got the 1 plus 1 over 1, we got the 2. And then when we increased it here, we got the 3 over 2. And then the 5 over 3. And then the 8 over 5. And then the 13 over 8. And so on. Okay. Wow. It's pretty rigorous mathematics here. Finally, the golden number phi. All right, let's try to give a a definition of this golden number phi. All right, so here I have a rectangle. All right, and pretend that this wasn't. This right here is the Greek letter phi, or some people say phi. This is a Greek letter phi, but let's pretend that this was an x right now. So this rectangle has a proportion 1 to x. So phi is that number such that, so this side would be phi, even though I'm saying 1 to x. This side would be phi if I could partition this rectangle into a perfect square, so 1 on all sides, all right? And the rest of this triangle would be similar. I'm sorry, I said triangle. The resulting rectangle would be similar to the original triangle. Okay, so even though this right here is a perfect square, the leftover part is perfectly similar to the beginning triangle. So phi is that number that gives me that ratio. Okay, So here I have 1 to phi, all right? And here I also will have that same similar ratio between these two, okay? And I can continue that. I can take this new rectangle and chop that up as well. And I can continue that forever. So we call this something like a golden rectangle. So if you can picture this, this original rectangle is my beginning, and here I partition it into a square. Okay, so this side is 1, this side over here would be phi, and this would be the resulting rectangle that is similar to the entire original rectangle. And then I can take this rectangle and make a square, and the leftover rectangle would be similar to not only this triangle, this rectangle would not only be similar to itself, but the second rectangle and the original rectangle. We can keep on spiraling down. That's what we mean by the golden number, the golden rectangle. All right. So coming back here, if it's true that these two gold or yellow rectangles are similar to each other, then I should be able to pull this relationship down. Okay. Oh, forgot I had the slide here. So phi is to 1 as 1 is to phi minus 1. You can see it there. So this short side is to the long side as this short side is to that long side. There we have. And cross multiplication, solving this equation, leads us back to find a number such that 1 more than the number is equal to the square of the number. That number is indeed, see, it's the same equation, right? If we cross multiply, we'll end up with something like this. And that number is indeed phi. It's equal to 1 plus root 5 over 2. So if we evaluate this, so I'm going to clear this, and I'm going to build this 1 plus root 5 over 2. Okay. All right. And I have my calculator set into the mode to always return me exact values instead of approximate values. That's a mode that could be toggled. Or when instead of hitting equal, if I hit shift equal, it will give me an approximate value when I build it. Or I can also just hit this button after I build it. Either way, okay? So we have our familiar friend here, this 1.618 guy, all right? So when asked this question, find a number such that 1 more than the number is equal to the square of the number, the answer is phi. There's 2 answers. We call the other answer little phi. We have a big phi and a little phi. But typically when we say phi or phi, we mean this number here. So actually it's actually 1 plus or minus the root 5 over 2. And those are my 2 solutions. This is indeed a quadratic equation. We could originally solve this situation using a quadratic formula. Okay. All right. So let's review our multiple connections here. So we talked about multiple representations. We looked at symbolic, we looked at verbal, we looked at tabular or numerical. We talked about nested radicals, continued fractions, Fibonacci sequence, and the golden ratio number. Let's see here. There's another feature on this calculator. It's quite strong. Okay, let's go in this mode here. Since we talked about this equation being a quadratic, it's the equation mode. This can solve multiple different types of equations. It can solve cubics. It can solve quadratics, which I want to solve. So I'll pick this quadratic function here. So here I just have to be aware of what these coefficients were. So for us, this was 1, because we had 1x squared. B would be a -1, and C would be a -1. Okay, so if I pick 3, I will need my A, B, and C coefficients and this constant. So I have a 1, I have a -1 for B, and I have a constant for C of -1. And if I ask my calculator to solve this, it indeed returns one of my answers as phi, and the other answer below is little phi, 1 minus √5/2. So it gives both solutions, okay? All right. Let's see. And that ends our presentation. I hope you enjoy the presentation, and make sure you check out this little dynamo, this 115ES Plus emulator. And now I will return you back to Tom, our facilitator for tonight. Okay.
Nevels, thank you very much for a fine presentation. You did a great job of picking outstanding examples, taking a very basic problem and looking at it from a number of different perspectives. I really like what you did with the nested radicals and tying that into the continued fraction and then going to the Fibonacci sequence. And then also at the end, pulling things together and making all the connections, because these are definitely things that we are trying to emphasize as we address the Common Core state standards in the future in our classrooms and in the world of mathematics in the United States. So thank you again for doing an awesome job with this. I learned quite a bit.
Thank you, Tom.
That concludes our presentation for this evening. For those of us who attended, thank you all for coming, and we hope to see you here at a future Casio webinar.